Okay, Newton's third law. So one of my favorites. I guess when I started teaching physics, that I thought this was kind of a simple law, and I enjoyed the math of the second law with the acceleration is force over mass. But so I've gotten deeper into physics. I think I enjoy the third law most of all because it's a source of I don't know how he came up with this back before as much was easy to measure and was easy to understand. It really makes me realize how brilliant an idea this was at the time. So let me see if I can get across the idea. So this Newton's third law says that for every action is an equal and opposite reaction. So action reaction pairs, yeah, kind of, but to me, that it really says that forces come in pairs. Always, every single last force is going to have a partner someplace that's going to be equal magnitude and point in exactly the opposite direction. So let me walk you through what this looks like and what this means. So suppose I have just a box. The box that's sitting there. So I can think about this. I'll think about this in two dimensions. So my vertical dimension and my horizontal dimension. So my vertical dimension, hopefully it's not too much of a leap to say, okay, my vertical dimension, I have gravity pulling it down. So I have the field force of gravity acting at a distance, pulling it down. And I'm going to have a normal force pushing up, and those two are going to be equal and opposite. But these are really not a pair in the way that Newton was describing it. So these are two different things, and they each have other partners. These are not the partners. These are sort of half of a pair that happen to be acting on the same box in opposite directions. So what's the second pair of this? Well, gravity is being pulled down. This box is being pulled down, and way down in the center of the Earth, right, the Earth is being pulled up towards that box, right? So one pair is going to be these two. And then I'm going to think about a contact point. So what's this other pair? So this is the tabletop pushing up on the box, but the box is pushing down on the tabletop. So I'm going to have an effective force acting on this tabletop that's going to be the second pair to this one. Yes, it's coming from gravity, but we'll get into that later. So the key with this is recognizing that oftentimes we ignore the partner for a pair. So forces come in pairs, yes, but almost never do we deal with both of them at once. We deal with the forces that are acted on a single object and try to make sense out of it. So I'll try to explain this as we go further along. But the key things I'm going to think about, in the same way as we're identifying forces, we're going to think about, well, touch points. So what's happening at a contact point, and then acting at a distance, and the things that act at a distance in physics are field forces. So in this case, it's mostly going to be gravitational field, but it'll be true for electrical fields later, and magnetic fields if you get into physics C as well. Okay, let's take something a little bit more complex. So here I have a mass. So let me think about these pairs of forces that are acting on it, right? So, well, I'm going to have gravity pulling it straight down. So here's my mass. I'll say I'm going to have gravity pulling it straight down. Right? I'm going to have the normal force acting on the box in that direction. And I'm going to have some string. I'm going to assume this is frictionless. I don't want to deal with it, or stationary. I don't want to deal with it. So I'm going to have a string, and this force I'm going to call tension going in this direction. So it's a little more obvious here that the force of gravity is not the partner pair to the normal force, right? That's not it at all. So the partner pair for the force of gravity is way down the center of the Earth. The Earth is being attracted to this mass a bit. Right? A normal force coming from this is coming due to some fraction of gravity, but the normal force is coming from the mass pushing perpendicularly into the floor. And tension, right? So where's my partner force for tension? Well, you get to decide, right? So I could say the other part of tension is coming from up here. And strings, right? So this would be my partner pairs for tension, right? So at this contact point, I have the tension on the string pulling one way, and this contact point, I have the tension on the string pulling the other way. And strings are kind of interesting because I can randomly put my point here, right? So what's happening here? Well, I've got the same thing. I've got a force pulling this direction and a force pulling in the opposite direction. So strings are something that transmit force. Yeah, so it pretty. I find it a fun way to think about strings. So a string transmits a force from one place to another, and those force pairs are wherever you feel like chopping that string up. So the force pairs will come from that. So again, what we're looking at though, oftentimes we'll look at a single object and we'll say, well, what are the forces acting on that object? And those forces acting on the object are not force pairs. They're going to be halves of these force pairs. So the fun part about this is there's always another force someplace else. So let's go through a little bit and think about some other situations we might have. So here we go. Let's take a couple of blocks, because why not? We love blocks. And I'm going to push on the blocks this way. And I'm going to have a whole bunch of contact points where I could think about force pairs, right? So I'm going to think, well, what's happening at this first contact point A, right? Well, for any contact point, if there's a force push in one way, there's an equal and opposite force push in the other way. So here we go. So this means that if I'm pushing on the box, regardless of what else is happening, and importantly, regardless of what else is happening, that box is pushing back with the same amount of force. Right? So at this contact point, so at point A, here's my point A, right? I'm going to have my applied force, and I'm going to have some normal force from A pushing back. Let me think about B. What's going to happen at point B? Well, again, my box, I'll call this box 1 and this box 2. So my box 1 is pushing against box 2. So at this contact point, I'm going to have, so I'm going to call this B, point B. I'm going to have my box 1 pushing on 2, and I can try to put subscripts in there, try to indicate this. And I'm going to have the force of box 2 pushing on box 1. And to be fully correct about this, I should say these are equal, and these, of course, were equal to each other as well. So my force pairs at contact points are a little bit easier to find. So I'm going to look for things that are adjacent to each other. So at contact points, it's a little bit easier to find. What else did I want to say about this? And then at distances, it's a little bit more of a challenge, right? So here I've got a contact point, right? So I got the weight of the box acting at this point, pushing it down, and the normal force pushing up, right? So the floor is getting pushed down by the weight of the box, and the floor is pushing back with the normal force. And the same here, I'm going to have the weight of the box pushing down and the normal force pushing up. Okay. So contact points are going to have force pairs, but also remember that gravity, the pair for gravity is way off in the distance. Okay. Let's make it a little bit more complex. That's what we like to do. So let's put a string in here. So let's think about what's happening at this string. So if I apply a force, let's pull it this way. So we're going to pull this. I'm going to apply a force. This is my force applied. I'm pulling in this, and I'd say we're going, it's constant, constant acceleration. So it's there's no friction. So let me think about box 1 and box 2, and what's in between. So I'm going to think about now. What is this point here? So I'll go backwards A. What is this point B? And what is this point? We'll call this C. And so what are the forces acting at these points? So again, I'm going to think for any place that's a contact, right? So at point A, I have my applied force pulling in this direction. And I have the force that box 2 must be applying in the opposite direction. And this must be equals, right? So this is going to be the force of box 2 on A. And these are equal, right? So if you're pulling something, you feel the weight, right? You feel that thing dragging behind you. You got to fight it, right? So you're applying a force, and the thing's always applying an equal force in the opposite direction. At point B, what's happening at point B? Well, similarly, I'm going to have this box is going to be pulling on the string. So I'm going to have a force of 2 on the string. And I'm going to have the force of tension from the string, which is going to be the string acting on the box. And again, these are going to be equal. And notice that I'm going to go over to point C. And I'm going to have similar forces. So I'm going to have tension. So this is going to be the same magnitude of tension here. Remember, the string transmits my force, right? It doesn't use any force. It transmits that force. So I'm going to have the tension of the string on 1 now, and then going in the other direction, I'm going to have the force of 1 on the string. And these are going to be equal. Right? So, so notice a few things, that if we sum our forces, so if we add together all the forces, notice that my string force cancels out. It's the same magnitude but in opposite directions. Right? So a lot of times we'll say that internal forces really don't matter because they cancel out. And so here's an example of that. If I add together all these forces, what am I getting rid of? Well, I'm getting rid of my string tension in here, and that's just not going to have an effect on things. So anyway, a good way to think about these things. So I don't think I'll go into this longer example, but it's the same idea. So notice that my tension here will be different from my tension here. So I'll call this T1 and this T2. If I'm pulling it this way, and I'll go into some box examples, but it can be a little bit different. And then finally, we'll get into examples of things that are stacked. Again, you can work your way through this thinking about contact points. So what's happening at each of these contact points, and drawing a free body diagram at each contact point to make sense out of it. Anyway, hope that helps. We'll talk to you soon. Bye.